Okay, so in this video I want to talk about another basic concept with two-dimensional vectors, and that's the direction of a two-dimensional vector. The direction of a 2D vector, two-dimensional vector. Which way does the vector point? Okay, so there's two schools of thought on the direction of a vector. One is just describing the direction as an angle. All right, so using an angle to do that. Let me show you an example. Let's say we want to determine the direction of the vector. Let's say -5, -3. Okay. So this vector -5, -3, a 2D vector. How can we describe the direction that it points? Well, one way would be to, let's draw the vector. It goes left 5 and down 3. So left 5 and down 3. So I'll start over here maybe. And I'll say it goes left 5 and it goes down 3. So it starts here and terminates there. So the vector looks like this. All right. How can we describe that direction? Well, one way of describing the direction is with an angle. And so the way you do that is you assume the typical conventions that you do in trigonometry, in 2D trigonometry, where you use a coordinate plane sort of setup. So the vector starts here. So I'm going to set up my coordinate plane here. And right here is my positive x-axis. We know in the coordinate plane that the positive x-axis is the 0 degree mark. 0 rotation is typically considered to start there. And so this vector requires this much rotation from 0. And so one way we could describe the direction of the vector is to name that angle from 0. And typically you're going to use the positive direction to get there, not the negative direction, okay? So let's call that angle theta. We're interested in determining this angle theta. So how could we do that? Well, maybe the easiest way is to use reference angles. So if you want the reference angle is right here. This purple maybe doesn't work very well. Let me see, no. Let's try this other one. The reference angle right here is theta bar. We denote reference angles as the same variable, the same letter as we do for the angle, but put a bar over the top. And so the reference angle here, using some basic right triangle trigonometry, is theta bar equals, and using the right triangle just by itself, we consider these sides to be positive, because the reference angle doesn't depend on negatives at all. Theta bar is going to be the inverse tangent, or the arctangent, of the opposite side, 3, over the adjacent side, 5. So again, the reason you use positives here for your reference angle is because this right triangle could live in any quadrant and the angle would still be the same as a reference. Okay? So if we consider this reference angle, and we want to know what it is, we could use our calculator. Oftentimes, vector direction is given in angles, so I'm going to make sure, degrees. So I'm going to make sure my calculator's in degree mode, and I will type tan inverse of 3/5 and see that my reference angle is about 31 degrees. Okay, so that's my reference angle. So how can I use that now to find theta? Well, theta rotates to 180 plus a little bit more. So theta is going to be 180 degrees plus my reference angle 31 degrees, which is 211 degrees. And so oftentimes we will describe the direction of a vector using this angle measured from the positive x-axis. If you orient your origin at the initial point, the origin, if you will, of the vector itself. Okay? So 211 degrees, that's the direction of this particular vector. Now, another way to describe direction, let me just erase all the parts we don't need. We won't be using this now as our way of measuring, so I'll erase that. Okay, we'll still use the same theta bar, okay? But lots of times, you might want to describe the direction of the vector like in a navigational sense, right? Using north, south, east, and west. So the way we might do that is using what we call bearings. And I've discussed bearings in a different video, so I'm not going to go into that. But this particular vector points in a southwest direction. So our bearing setup is going to be south, some angle, west. And so now what you need to do is when you draw your coordinate plane here, it's actually a compass where this is north and this is south. And the angle that goes here is, if you start at south, which is this south line here, how much rotation does it take to the west to get your vector? So in that case, we need this angle, which is going to be, well, here, this is 31. And I know that these two angles together make a 90. So all I have to do is take 90 degrees minus 31 degrees. 90 degrees minus 31 degrees, which equals 59 degrees. And that's the angle that goes here in our bearing, because that's how far west of south this vector travels. So that might be a way to describe the direction in a navigational sense for a vector. Okay? Now, what if your vector points exactly east, west, north, or south? You know, it doesn't lie in a quadrant if you're considering the coordinate plane. It lies on an axis. Those are easy. You simply say the direction is due north, due south, due east, or due west. Okay? And that's all there is to it. All right, so that's the direction of a two-dimensional vector.